All right, section 5-4 is on Riemann sums and the definition of definite integrals. The objective of this section is to use Riemann sums and limits to define and estimate values of definite integrals. You've already done that in the first part of this section. You've used Riemann sums to approximate the definite integral by calculating the areas of rectangles and summing those up to give you an approximation for the definite integral. And if you recall, there was one special Riemann sum that you saw there. That was the midpoint Riemann sum. And what distinguishes one Riemann sum from another is the fact that you get to pick the location of that sample point in each subinterval to determine the height of the rectangle. And so we called it a midpoint Riemann sum, of course, because we were picking the midpoint of each subinterval in order to determine the height of each rectangle. So let's start out by looking at the other four. There's a total of 5 here that we need to talk about. The other 4 special Riemann sums. So let's start with this first one here, which is a left Riemann sum. And as the name indicates there, we're going to pick the sample point by choosing the left side of each subinterval. So let me just sketch a function here, and we'll just illustrate this with a little sketch. We'll call this f of x, and we'll just make some interval here from a to b. And let's split this up into a couple of subintervals here. I won't worry about sketching all these, so I'll just say dot, 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 all the way up to the very last subinterval there. Okay? And then again, we're going to pick this sample point in each subinterval, in this case on the left side of each subinterval, to determine the height of our rectangle. So let's name this first sample point right here will be at C1. It's actually at A. And that point right there will determine the height of that first rectangle. So by sketching that first rectangle, it would look something about like this. And then we'll pick, this will be C2 at the left side of the second subinterval, and so this point right here will be used to determine the height of that second rectangle. So that gives us a second rectangle that looks like this. And we'll continue with this. This will be C3 at the left side of the third subinterval. So this point right here will be used to determine the height of that third rectangle. And we end up with a third rectangle that looks like that, and so forth, all the way up to the very last subinterval. We'll name this point right here as C sub n. So this point right there is used to determine the height of that last rectangle, so that gives us a rectangle that looks something like this right here. Okay? And that right there would be a left Riemann sum, using the left-hand side of each subinterval to determine the height of each rectangle. All right, the next Riemann sum, if we have a left Riemann sum and a midpoint, it probably makes sense that we're going to have a right Riemann sum, and that's in fact the next one for us to consider here, is the right Riemann sum. Let me again sketch this for you. So let's say we have a function, and we'll pick some subinterval here from a to b on this function. And again, I'll just split this up into some subintervals. And I'll say dot, dot, dot to indicate that continues all the way to the last subinterval. And so now, because it's a right Riemann sum, that means we're going to pick the right-hand side of each subinterval to determine the height of each rectangle. So over here in this first subinterval, right here will be C sub 1. And so that will correspond to this point right here, which you can see corresponds to this rectangle right here that we end up with. And in our next subinterval here, this would be C sub 2, the right-hand side of it. And so that point right up there is going to determine the height of my next rectangle. So my next rectangle looks like that. And then finally, C sub 3 here in the third subinterval, would correspond to this point right up there. And that gives us a rectangle that looks something about like this in that third one. And this continues then all the way up to the very last subinterval. So we'll call this one C sub n. Notice that C sub n is the same value as b actually in this case. And that corresponds to that point right there on our function. So the height of that last rectangle looks something about like this. All right. And there's our right Riemann sum. We use the sample point from the right side of each subinterval to determine the height of each rectangle. So we have a left, we have a right, and we have a midpoint. Now with the midpoint, we have a special name that we use, m sub n, as you saw. With left and right, we don't have special names. for those. Those are just Riemann sums, so we just use R sub n for each of these. I shouldn't say that is a special name, but this is the general name that we use for all these. So we'll use R sub n for a Riemann sum of any sort, as you saw in our little proof that we did with, well, not proof, but really our formula that we came up with used R sub n. So both of these use R sub n. All right, and finally the last two. You've seen left, you've seen midpoint, you've seen right, and the last two for us to consider are what we call the lower Riemann sum, which probably that gives you a hint as to what the last one will actually be called. But the lower Riemann sum means that, again, the difference between these is where we're picking our sample points. So a lower Riemann sum means I'm going to choose the lowest point in each subinterval to determine the height of the rectangle. So let me sketch a function here. I'm going to put a little bit more of a curve to our function here so that we have a little bit more interesting thing here to look at. So we'll say that this is our function, and let's split this up into a couple of subintervals here. Let's go from A here to B, we'll say, is this. And we'll split this up into one. Actually, let me make that a little bit wider here in that subinterval. Redo that. I don't want to be those aren't quite equally spaced, but they're close enough for us. Assume those are equally spaced apart. And even if they're not, it doesn't matter. You can still do a Riemann sum on this thing. But let's take this function here and look at the lower Riemann sum. So again, the point that you're going to pick for each sample point is going to be choosing the lowest point on the function in that subinterval. So for this first subinterval here, I can see that over here on the left side of that subinterval, there's the lowest point. So that'll correspond to C sub 1. And that will give me a rectangle then that looks something like this for that first subinterval. On the next subinterval, I can see that I actually had a maximum somewhere in, not quite maybe the middle, but somewhere over here, I would say, is about the maximum. It might be close to the middle. Doesn't necessarily have to be the middle of that, but looks like it's technically just to the left of that where we hit that maximum point. That's the highest point on that function. Oops, I'm sorry. We're doing a lower Riemann sum. Let me take that back. Let's try that again. The lowest point I can see is over on the right-hand side. So that's C2. And so that gives me this rectangle that would look something about like this. Again, you can see that my rectangle is completely below the curve when I do this. On the next subinterval, it turns out the right-hand side, again, is the lowest point. So this would be C sub 3. So this would be my rectangle right here. On the next subinterval, looks like it's the right-hand side again. So again, you'll notice that the first subinterval, we used the left-hand side, but that was when the function was increasing. Now when the function is decreasing, we're using the right-hand side to get the lower Riemann sum is what we're actually seeing happens. Now here on this subinterval, you got to be a little bit more careful because I tried to sketch it so that the lower bound here actually is somewhere in the middle of this thing. It might not necessarily be right at the middle, but we'll say it's about right here is that lowest point. So that gives us a rectangle that looks something like this. And then finally for the last subinterval, it looks like the left-hand side now because our function's increasing again. This would be C sub 6. Okay. And obviously you continue on from there depending on how many subintervals you have, but each subinterval you got to take each one individually and look at whether where the highest or lowest point in this case is at. So there is our lower Riemann sum, and because of the fact that it's a lower Riemann sum, we're going to use L sub n to indicate it's a lower Riemann sum. So we use a special name there for a lower Riemann sum, L sub n. All right, we have the lower Riemann sum. So probably the last one here isn't much of a surprise. If we have a lower Riemann sum, we also have an upper Riemann sum. And so this is named U sub n. So we have a special name for upper Riemann sum, lower Riemann sum, and midpoint Riemann sum. And just like we saw with the lower Riemann sum, we call it a lower Riemann sum because you pick the lowest point in each subinterval. This is the opposite of that then. This is called an upper Riemann sum because we're going to pick the highest point in each subinterval to determine the height of our rectangles. So again, let me sketch a curve similar to the one that we just had here, and I want to kind of carefully sketch this thing actually so that I have some interesting points to put in here for us. But we'll say that this goes from A to B, and we'll say that this is our first subinterval. Here will be our second subinterval. There will be our third. Here's our fourth, and here's a fifth and sixth. Okay, that's close to the same curve we had a second ago. And now for each subinterval, again, you pick the highest point in each subinterval to get your upper Riemann sum. So in the first subinterval, it looks like it's over on the right-hand side is where we have our highest point. So this right here would be C sub 1. And that would give us this rectangle right here. All right. For the second subinterval, the highest point, now this time I tried to make it so the highest point again was somewhere inside in that second subinterval, not necessarily in the middle, but somewhere in between the left and right hand side there. And so this rectangle would look something like this then. And then C sub 3, for the third subinterval, looks like the highest point is now on the left hand side. That's C sub 3 is right here. So that will give me this rectangle. And again, you'll notice with an upper Riemann sum then that all of our rectangles are above the curve. The curve is completely enclosed within that rectangle. For the next subinterval, looks like the left-hand side again is the highest point. So this will be C sub 4 over here. That will give us this rectangle. Now this next one looks pretty close here, but it does look like on the right-hand side is where I have the highest point there on my sketch. Yours might look a little different depending on how you sketched yours there. But on mine, it looks like on the right-hand side is where I hit the highest point, so that gives me this rectangle here. And then finally, again, on the last subinterval here, it looks like on the right-hand side for sure is the highest point, so that turns out to be C sub 6 over there on the right. And that gives us this rectangle right here. There's your upper Riemann sum. We call that U sub n because the fact that it's an upper Riemann sum, again, you'll notice that all of your rectangles completely are completely above the curve. In other words, the curve is completely enclosed within that. Versus a lower Riemann sum, if I just slide back up here, we call this L sub n, and notice that all of your rectangles are below the curve. So the curve, the area below the curve completely includes the rectangle in this case. All right, so we call those our upper and our lower Riemann sums. And depending on the problem there, depends on which one they might ask you to calculate, and just depends on your curve as to how carefully you have to calculate these upper and lower Riemann sums. If your function is strictly increasing or decreasing, turns out the left and right Riemann sums would be the same as the upper and lower Riemann sums. Here where our curve kind of changes direction, it's increasing, then decreasing, then increasing again, you got to be a little bit more careful when you do that. All right, one thing to note here then, we just learned the lower and upper Riemann sums, and you've already seen the notation we use for any Riemann sum, R sub n. It turns out that for any Riemann sum that you calculate on a given subinterval for a given function, using the same number of subintervals, turns out that R sub n is always going to be in between your lower Riemann sum and your upper Riemann sum. L sub n is less than or equal to R sub n, which is less than or equal to U sub n. Now the significance of this is something we weren't able to do with trapezoids. With trapezoids, we knew we were approximating area, but we could never really tell how close we were actually getting. We could tell whether it was an underestimate or an overestimate, depending on your curve. You can look at the curve and determine that. But again, we still really never knew how far we are off. The nice thing about the lower and upper Riemann sum is they give you a lower bound and an upper bound for your Riemann sums. You know that for any calculation of a Riemann sum you do, it's always going to be between these two values here. So by using more and more subintervals, or that is by using smaller and smaller interval widths, it turns out that I can get closer and closer to the actual value. And not only can I get closer and closer to it, just like with trapezoids, but I also can use this to find out how close I actually am. I know that I'm always going to be greater than the lower Riemann sum, but less than the upper Riemann sum. I know that I can kind of squeeze that interval and get closer and closer to the actual value that I'm looking for. And I'll know how close I am. So with that, we have this term that we use to describe functions that are meet this certain criteria here. This is called, the term here is integrable. Just like we use the term differentiable to talk about a function and whether or not we can differentiate it and evaluate it at a point. We have a term integrable that we use in a similar fashion, although the definition is a little bit more complex. It says a function in which the following occurs there has this property of being differentiable, or excuse me, integrable. The definite integral from a to b of f of x dx has to be equal to the limit as delta x goes to 0 of L sub n. Now that's saying delta x is the width of each subinterval, so you're letting the width of each subinterval get smaller and smaller and smaller, or that's the same as saying n is getting bigger and bigger and bigger. The number of subintervals is going to infinity. If it turns out the limit of the lower Riemann sum is equal to the limit of any Riemann sum, R sub n, which is equal to the limit of the upper Riemann sum, then it turns out your function is integrable. All right, and basically for most functions we're going to study, we're going to have this property. Okay, if your function is not bounded, in other words, it goes to infinity, those are types of functions where this property isn't going to hold. Or if you have a discontinuity in there, you can have problems with this as well. Okay, so you do have to watch out for those types of things that show up in your function, but otherwise, for the most part, our functions are going to be integrable. All right, let's go back to example 1. We started example 1 in the first half, but we only did part of it. It says for the integral from 1 to 4 of 1 over x dx, complete these steps here. So we're trying to integrate from 1 to 4, 1 over x dx. And it says for part A to find the lower Riemann sum and the upper Riemann sum and the midpoint. Now we've already found the midpoint, so we're just going to find the lower and the upper Riemann sum. That's basically what we're going to do. And let me draw a sketch again of this function from 1 to 4. So here's what 1 over x looks like. And we'll say that this is 1, and we'll put 4 out here. And so this will be 2, and we'll say that's 3. So there's kind of what that function looks like. Sometimes a sketch might help you out here. And we're actually going to find u sub 6 and L sub 6. So we're going to split this up actually into 6 subintervals. I have it split up into 3 right now. Let me split each of these in half. And we'll get ourselves 6 subintervals. So this is actually at 1.5, 2.5, and 3.5 are the endpoints of those other subintervals. And so let's start with the lower Riemann sum, L sub 6. Remember that for any Riemann sum, it's the width of each subinterval, the delta x. In fact, let me start out by calculating delta x here. Delta x, remember, we already did that for the first part of this example, and of course delta x is going to be the same. But remember, it's b minus a over n to calculate that. So in our case, it's 4 minus 1 divided by 6 subintervals. That's 3 over 6. That's 1/2. Okay, so I know delta x for this is going to be 1/2. So it's going to be 1/2 times, and that's the sum of a bunch of y values. Okay? And if we're doing a lower Riemann sum, that means I want to pick the lowest point in each subinterval. So I'm going to do this with blue here. In the first subinterval, it looks like the lowest point is at 1.5. So this would be that first rectangle. In the next subinterval, it looks like it's going to be at 2. That's going to be my next subinterval there. And for the next subinterval there, it looks like the next rectangle is at 2.5 and so forth. All right, all the way out to the very last subinterval. The lowest point is on the right-hand side again, so I get that rectangle there. You can sketch in the rest if you want to. But now I can see what y values I have to calculate. I don't have to worry about what's happening at 1. Notice I didn't use the x value at 1, or the value of x equals 1 to determine the height of that first rectangle. It's at 1.5. So it's my function at 1.5 is the first y value, plus my function at 2, plus my function at 2.5, and since these are always on the right-hand side, once I know my first value, 1.5, adding my delta x, the 0.5 gives me the rest of the x values there that I need. all the way up to my function at the very last value, which is at 4. Okay. Now again, once you have that calculated, or once you have your formula written down, you can then use your calculator to help you calculate this. And you can either do that from the home screen, or you have a program you're going to use. And I demonstrated this the other day, but I'll show you it again. So let's run our Riemann sum program. It looks a lot like your trapezoid program. I've got an equation. Oh, actually, I don't have an equation in y1. Let me stop that and go back and do that. In y1, I need to put in the equation 1 over x, my function that I'm working with here. Let's try running that program again now. So I have an equation in y1. Obviously, if I had just a set of data, that I put the x values in list 1 and the y values in list 2, and I could choose the second option. But we're going to run an equation here. It's in y1. I'm starting at 1, and I'm ending at 4. Notice that you use the endpoints of your original definite integral over here. So I'm going from 1 to 4. Don't use the values that I put into my formula of 1.5 all the way up to 4. That will give you obviously a different result. And then we're going to break this into 6 increments, or 6 subintervals, 6 rectangles, however you want to describe that. Now we're actually calculating a lower Riemann sum, but notice that if I go back to my sketch here, my lower Riemann sum is actually using the right-hand side of each subinterval. So it turns out my lower Riemann sum is the same as a right-hand Riemann sum. I can see that in my sketch. So I can tell it to actually calculate a right Riemann sum. Just happens to be that's also going to be the lower Riemann sum. It's already crunched the numbers. It shows me my formulas I need. You need to write those down. Of course, filling in all the values like I did with my formula. And finally, it shows you the results here. So R sub n, actually it's L sub n for us, but it's 1.218. 1.218. All right. Oops, let's write down the next one for us, and then we'll let our calculator crunch it. So the last one that we want to calculate it is U sub 6, the upper Riemann sum. So that's going to be 1/2 times. Now again, it's the sum of a bunch of y values. Let me go back over here and look at our graph here just to help us figure out what we got to do. But if I want an upper Riemann sum, that means in each subinterval I pick the highest point. So over here on the left side of that first subinterval is going to be the rectangle I want to create. And in the next subinterval, I'm going to use the left side of it as well. In the next subinterval, I'll use the left side of it to determine the next rectangle, and so forth. All the way up to the very last subinterval, use the left side again to determine the height of my rectangle. So in this case, it turns out the left-hand Riemann sum is going to give me the upper Riemann sum as well. So it turns out I've got my function at 1 plus my function at 1.5 plus my function at 2, all the way up to my function at 3.5. So you'll notice the difference between these two formulas is in the second case here for the upper Riemann sum, we're including f of 1. We're not including that in L sub 6. And in my lower Riemann sum, I'm calculating f of 4 at the very end versus I'm leaving that off for my upper Riemann sum, U sub 6. So the formulas are very similar. But let's let the calculator crunch that here for us. We'll run that again. Going from 1 to 4 using 6 subintervals. And again, this time the left Riemann sum gives us the upper Riemann sum. And so we get 1.593. And so there's our lower Riemann sum and our upper Riemann sum. Again, the nice thing about these two values, I know that the answer is then somewhere between 1.218 and 1.593. Versus with any other calculation that I was doing, I really didn't have an idea of how far off my approximation was going to be. At least I know that the answer is definitely between these two values. All right. And we've already answered part B there for example 1. So that's the end of our notes here for this section.